So, our topic for today is dimensionality reduction using the method of principal components analysis. Okay, short form we write that as PCA. So, this is what we will be discussing in this lecture. Now, we already introduced the basic theory that is behind the principal components analysis. In fact, we say that the basic objective is to have a reduction of data. I mean, if the input data that we are having is m dimensional, okay, we should remap this input data into a lower dimensional space, okay, in such a manner that we can eliminate, I mean, in that mapped space we can eliminate those components which are contributing to very low variance. Okay. So, that was the idea. So, what we said is that we have to design the best kind of a transformation T which can do this kind of a job, that so that if x vector is mapped into Tx vector, or where T is an m by m matrix, okay, the basic idea is to find the matrix T. And what we did in that process is that we decided to project this vector x, okay, onto a set of vectors, okay, onto a set of m dimensional input vectors, okay, which we called as QIs. So, we were projecting that into QIs, and then the solution that we had got under the extremal case, okay, mind you, we said extremal because there we did not specifically, I mean, in fact, I mean, as very rightly pointed out by one of the students, that the extremal does not necessarily mean that it is a minimum, okay. We derive the condition of extremality, okay, of the variance, and that condition led to the solution that the solutions that we are having, okay, basically boils down to the solution of the eigenvalues of the co-occurrence matrix R. Okay. So, by having the correlation matrix R, okay, and finding the eigenvalues of that, where lambdas are the lambda i's are the eigenvalues, and their corresponding eigenvectors, okay, are the vectors onto which we would like to project the input vector into those vectors. Okay. So, the thing is that the solution naturally is obtained for m number of eigenvectors, because if our correlation matrix is of size m by m, in that case we are going to have m different eigenvalue solutions for that. All right. So, the thing is that I mean, unless we definitely know that how to reduce the dimensionality, okay, we should first accept that, okay, I mean, till now we haven't saved anything. We had started with m dimensional x vector, and after projecting into the eigenspace, we have got m such different unit vectors which are possible, q1, q2 up to qm. Those are the m different vectors that we have, unit vectors we have, to which basically this x can be projected. And another very important result that we had obtained there was that the variance, I mean, we had used the Qj as a variance probe. Okay. So, we used this thing as psi of Qj, where psi was used as the variance probe, and we had shown a very important relation that psi of Qj is equal to lambda j, okay, where lambda j is the jth eigenvalue. So, we definitely have such things done for j is equal to 1, 2 up to m, since there are m such eigenvalues. So, this is very interesting to note that what is psi of Qj? It is the variance probe. So, the variance is equal to the eigenvalue. So, that means to say that if we can, okay, arrange the eigenvalues in a descending order, that is to say lambda 1 being the highest eigenvalue, lambda to the next one up to lambda m being the lowest of all the eigenvalues that we have got. So, if we can arrange the eigenvalues, okay, in a decreasing order, in that case we should be able to decide that, okay, if we decide to eliminate the last m minus l, where we decide to keep l eigenvalues and we decide to eliminate the last m minus l eigenvalues, in that case what we are essentially eliminating are the components with low variance, because now in the projected space, in the projected QJ space, eliminating low values of lambda j means that we are eliminating the components with low we are eliminating the components with low variance in the projected space, right. So, this we have to keep in mind, and now we have to talk about the way whereby we can do the dimensionality reduction. So, for that matter, what we do is that we have how many? We have got m possible solutions for the unit vector. So, there are m possible solutions for the unit vector q. Okay. So, there are m possible projections of the data vector. So, what we get is that if Aj is the jth projection or projection of the x vector into the jth unit vector. Okay. So, what we are looking for is by projecting this x vector into jth unit vector. So, what we have to do, qj transpose, okay, qj transpose x, that becomes the jth projected value of x into this qj, okay. And this can be also represented as, this is one and the same way of writing x transpose qj, right. And we have got, since there are m possible solutions, this we have to do for j is equal to 1 to m, okay, where Aj's are the projections. So, Aj's we call as the projection of the x vector onto the principal directions as represented by qj. And as Aj's are projections into the principal directions, okay, as Aj's are projection into the principal directions, this Aj is called as principal component. Okay, so, that is why the name principal component originates. Okay. So, basically we are going to have m such principal component. Okay. And out of that, which ones are very important to us, those are the things which we will be discussing very shortly. So, now what we have is that we have got this equation, call it equation number 1. Then this equation number 1 we are going to call as an analysis equation. So, equation 1 basically represents the analysis. So, what is meant by analysis? Where we are projecting x into a new space. We are projecting x into the qj space, and then the projections that we are getting are the principal components. So, this is called as the analysis. Okay. And our objective should be that if we can project these vectors into this qj space and do the analysis, we should be able to do the reverse of that also. What is the reverse of analysis? Synthesis. So, that means to say that in the synthesis, what we are going to do is that from these Aj's, okay, we should be able to recover the x. Okay. So, in order to recover that, so what we do is that since there are m such number of AJs, since AJ varies from j is equal to 1 to m, we can form a vector consisting of the projections. So, we can define a projection vector. So, we define a projection vector, call it as A vector, whose elements are going to be A1, A2 up to AM. There are m such projections. In fact, this in the expanded form one can write as X transpose Q1 vector. The second element will be X transpose Q2 vector. Like that, the mth element will be X transpose Qm vector. Okay, so we write it like this. Customarily, we should represent it with a square bracket. So, this we should represent as transpose. This also is transpose, and this is one and the same as writing it in the matrix notation as, I mean, we can write it as A vector is equal to Q matrix. Q matrix is something that we have already defined in the last class. How is the Q matrix formed? The Q matrix is formed using the QI vectors, okay, using all the QI vectors, okay, Q1, Q2 up to Qm, okay, we had formed the Q matrix, and Q matrix had got a unique property. What is that? It is a orthogonal matrix. So, Q matrix was an orthogonal matrix. So, we have got basically that A is represented, I mean, this is one and the same thing as the analysis only what we have done. So, basically there is no difference between our equation number 1 and if we call this thing as, let us say, equation number 1A, basically there is no difference. It is only combining all these j terms 1 to m, all these m different AJs are being combined in the form of a vector, and all the QIs are combined in the form of the Q matrix, nothing else. I mean, it is the same thing. Now, we do one thing. Now, we pre-multiply both the sides of this equation using Q. What will you get? If you pre-multiply both the sides, pre-multiply both the sides of equation 1A by Q. What are you getting on the left hand side? You are getting QA, and what are you getting on the right hand side? X. You are getting X. Why? Because it is QQ transpose, and QQ transpose is equal to the identity matrix, because Q matrix has been already proven to be the orthogonal matrix. So, that is why this is QQ transpose, I mean QA is equal to X. So, in fact, I mean X can be represented now as, I mean, in the expanded form we are going to write it as summation of AJ QJ vector, okay, for j is equal to 1 to m, right. This is the expanded form of the matrix equation that we had written in this step. It is just the expanded form of this, and let us call this thing as equation number 2. So, what is equation number 2 representing? Synthesis. So, the equation 2 represents synthesis, and in order to have a synthesis, what are our basis vectors for synthesis? The QJs act as the basis vectors for synthesis. QJs are the basis vectors for synthesis. This is a very interesting observation, that you see, unlike the typical orthogonal transform kernels that you use, Fourier, discrete cosine transforms, etc., etc., okay, you do not use any specific function as the basis function. Instead, you are deriving this, okay, by analyzing the correlation matrix. I mean, you are finding the eigenvalues of the correlation matrix, and the corresponding eigenvectors that you are getting are essentially forming the basis vectors. So, you are observing, I mean, you are forming the basis vectors from the random process itself. There lies the beauty. I mean, you do not have to depend upon any external kernel to do that. You are basically forming the basis vectors out of the correlation matrix of the same random variable. Okay. So, in that sense, I mean, this transformation technique has become very popular. In fact, it is used in many domains of signal processing. Okay. In fact, in the signal processing community, this approach of principal component analysis is very often referred to as Carhunen-Loewe transformation. Okay. In fact, I mean, people do not use their long names of Carhunen and Loewe. Okay. And there they use K and L. So, people simply call it in the short form as KL transformation. Okay. In fact, in the image processing community, okay, people follow the two-dimensional version of this, and there the transformation that they use is also known as the Hotelling transformation. This also is based on the same principal component analysis. Okay. So, in different variants it is available, and people have been using this approach. Okay. And essentially it is, I mean, its main use is dimensionality reduction, and because of this property of dimensionality reduction, it is used very effectively for the purpose of data compression. When we need to compress large amount of data, especially speech data, video data, which has to be transmitted over a very limited bandwidth, okay, there we essentially require this type of transformation techniques. Okay. Now, okay, still some doubts must be in our mind that, okay, this is a dimensionality reduction or data reduction, data compression type of techniques, then why are we at all covering it under the topic of neural network? Okay, till now that question must be cropping into our mind, which I will be explaining pretty shortly. Okay, just to show you that essentially the neural network, I mean, if we can construct a neural network using Hebbian learning mechanism. Hebbian learning is something that we had discussed much earlier, I mean, in the beginning part of our lectures. Okay. We have talked about, while explaining about the different learning mechanisms, we had talked about Hebbian learning. In fact, if we have a Hebbian learning network, okay, we consider a single neuron and we consider m inputs connected to that neuron, okay, it can be shown by analyzing mathematically. Okay. I mean, this was a very breakthrough result, one can tell, that it can be proved that using the Hebbian learning mechanism, the I mean, a single linear neuron, okay, essentially performs the task of finding the first principal component. What is first principal component? That is corresponding to lambda 1, because if we arrange the eigenvalues in the decreasing order and lambda 1 is the highest eigenvalue, then with lambda 1 we will be having an associated vector q1. Okay. So, it is, we are referring to the maximum eigenvalue. So, it leads to the maximum eigenvalue solution, okay, neuron which is learned with Hebbian learning mechanism. Okay. So, that is why principal component analysis problems, okay, can be very easily modeled using neural networks which follow Hebbian learning. That we will be discussing little later on, of course, without going into the details of mathematics, because the mathematics part of it will be fairly involved. Okay. It itself will cover quite a few number of lectures, and that may disturb the thrust of this course. So, that is why I will be only giving you some references, okay, from where I mean those who are interested in learning the intricacies of the mathematics can go through that. Anyway, I mean before we do all those things, okay, we have to first of all talk about the dimensionality reduction, which was in our itinerary for today. So, what we do is that we have got, I mean in the we can project the vectors, okay, into the QI spaces, okay, and we got all the different projections, and let us say we have the eigenvalues which are arranged in the descending order. So, we have got lambda 1, lambda 2 up to lambda L, okay, which denote the largest L eigenvalues of the correlation matrix R. So, lambda 1 to lambda L are the largest L eigenvalues of the correlation matrix R. Okay. In that case, we can approximate the data vector. Okay. See, the solution of the data vector x is, we know that already. I mean the synthesis equation says that you have to have summation of this aj qj, and this summation, mind you, please note here, is j is equal to 1 to m. All right. Only if we sum up for j is equal to 1 to m, then we can get back the exact solution of x. But now that we have got, we have arranged all our eigenvalues in a descending order, and the corresponding eigen vectors which are associated with it are q1, q2 up to ql. Okay. We choose the first L. Now, let us decide to truncate this summation series considering the first L eigenvectors only. All right. So, if we do that, means instead of m terms, we take the first L terms, naturally we are not reaching at the exact solution. So, whatever solution we find for x cannot be called as x anymore, we have to call that as x hat. So, this is x hat as vector would now be the summation of same thing aj qj only, but aj qj summed up for what? 1 to L, yes, j is equal to 1 to L, because we are taking the L terms, it is up to lambda L, please note. And this, I mean this is the summation representation, and the same thing can be represented like this also in the form of, I mean just showing in the vector expression itself, that we can write it as q1, q2 up to ql, all right. And then here we are having the A vector arranged as a column vector. So, q arranged as a row vector, and A is arranged as the column vector. Okay. And what is the relationship between L and M? L is less than M. Okay. In fact, in the limit, L could be equal to M also. If L is equal to M, in that case we are not doing any truncation effectively. So, if L is equal to M, then x hat becomes equal to x only, but in general when we happen to choose L to be less than M, okay, then x hat is different from that of x. So, this we are calling as the equation number 3. All right. Now, what now I mean how we can compute these ALs, that we already know, that in order to compute these ALs, first of all what we have to do is to project these x vectors onto, we need not have to project to all the m QIs, we can project them into the first L QIs. Okay. So, we can obtain the A vector as A1, A2 up to AL, this vector, okay, can be formed as Q1 transpose, Q2 transpose, okay, up to here QL transpose. Okay, this multiplied by the x vector, and this is for L less than or equal to M. So, this we can call as the equation number 4. All right. So, basically what does it mean? Okay. If we so that means to say that using the QIs, okay, we can transform the x vector. X vector is of original x vector's dimension is M. So, we will keep all the M elements of this x vector, but we will project all these M elements, or we will project the x vector together, I mean along with all these M elements, okay, into an L dimensional space, and those L dimensions are formed out of the QIs. So, we will take like this. So, we will be taking x1, x2 up to xm, okay, this is our input, and then this input will be transformed by this Q1 transpose, Q2 transpose up to QL transpose, okay, and mind you L is less than M. So, that means to say that this dimension is less than this. So, as a result of that, what we are getting is that this will get mapped into A1, A2 up to AL. So, from an M dimensional input space, we are getting an L dimensional A components projections. So, this much will be done by the encoder. Okay. This is our analysis part. So, the analysis part will be done by the encoder, which basically maps the M dimensional input space. So, we call it as RM. From RM it gets mapped into RL space, right. So, this is M to L dimensional transformation being done by the encoder. Okay. And in the decoder part, just the opposite of that is going to happen. So, there what we are going to do is that our input will be the A's, right, A1, A2 up to AL, that is going to be our input, and we have to transform it using what in order to get the x q vectors. Okay. Last time it was the q transpose, okay, and this time we are going to take the q vectors. Okay. So, if we take all the q vectors q1, q2 up to ql, okay, this ultimately gets transformed into x1 hat, x2 hat up to xl hat, and why hat? Again, because this is not an exact solution, this is an approximated solution, approximated because of the truncation of the L terms. All right. So, this is getting mapped into this. So, this is our decoder part. Okay. In fact, this way one can practically use this kind of principal component analysis, okay, for doing the encoder and decoder, and many practical image and video coders or speech coders, okay, can be realized using this principal component analysis technique. Now, the only difficulty that one can find about this is, the $1,000,000 question is that how to determine all these Qs, okay, practically. I mean, okay, it is easy to talk that we are talking in terms of the eigenvalues of the correlation matrix, but somebody has to really form the correlation matrix by making several observations of the input variable, and then finding the eigenvalues of the correlation matrix is also a computationally involved problems. So, let us not, Yeah, sorry. I mean, it should be, yes, somebody has very rightly pointed out, okay, that we are getting here up to XL, okay, and in fact, just see that it is XL only that, no, it is not XL, okay. Ultimately, we are getting the XM, so this is wrong, yes, yes, yes. Thank you for the correction, because this definitely, I mean, it will be clear if you look at the original expression only, okay. We have all these AJ, QJs, okay. Only thing is that we are summing up to J is equal to 1 to L here. J is equal to 1 to L we will sum up, okay. But this leads to an X vector, not an exact X vector, but an approximated X vector, but the dimension of X vector will be preserved, okay. So, what we are going to get is ultimately an M dimensional X vector only, but because it is different from the original X vector elements, so that is why I am writing it as x1 cap, x2 cap up to xm cap. Thank you for pointing this out. So, this has to be xm. Okay, I mean, let us come back to what we were discussing, that the encoder and the decoder structure looks pretty simple, okay, that okay, one has got this or one has got this in the decoder, and then one can easily do the transformation, because the transformation is nothing but a projection, and that is very easy to do. But the $1,000,000 question is that how to determine all these QIs, because finding the eigenvalues problem is a computationally involved problem. So, that is the reason why one has to study that whether this could be carried out using neural network or not. All right. Now, okay, before we go into the neural network implementation of the principal component analysis, okay, little bit of time we should spend at the error, because we have just now seen that what we are getting at the reconstructed thing is not the exact x vector, but it is the x cap vector. So, if we take the vector difference between the x and the x cap, okay, that is going to be our error vector. So, let us try to find out the expression for the error vector, and in fact, as expected, naturally, okay, I will not tell you that. I mean, you will automatically come to know when you find out the expression of that. You see, the error vector will be represented as E vector equal to x vector minus x cap vector, okay. And let us call this thing as, since we have gone up to equation number 4, let us call this as equation number 5, okay. Now, if we substitute the equations 2 and 3 into this 5, you see why we are looking for equation 2 and 3. Equation 2 says this, you see, equation 2 tells us that x is equal to summation j is equal to 1 to m aj qj, okay. So, if we now write it down, this is equal to j is equal to 1 to m, okay, aj qj. This is the substitution for this x, and the substitution for the x cap term is going to be, you see, x cap is summation of aj qj only, but j is equal to 1 to l. So, this is equal to j is equal to 1 to l aj qj, okay. And in this case, what we are having is that L is less than or equal to M. So, what we can see from this is that essentially this can be represented as, yes, somebody can tell me a compact way of representing this, summation j is equal to 1 to m and summation j is equal to 1 to L, and L is less. So, L plus 1 to m. So, I can represent this same thing as j is equal to L plus 1 to m Aj Qj vector. Okay. So, this is our error term, and now let us calculate the errors dot product with the x cap vector. All right. So, what are you expecting? Okay, just see what you are getting. This is I is equal to L plus 1 to m. I mean, we just simply substitute the expression that we have got for E. So, E is Aj Qj vector. Okay. And what is the next term, that is x vector? X vector's term is Aj Qj. In fact, here, okay, I mean, right, okay. This is Aj Qj, okay, j is equal to 1 to L. All right. Now, yes, somebody has already guessed that it is becoming 0. Okay. That means to say that error and the x cap vector, they are orthogonal to each other, okay, expectedly. In fact, I mean, you see that this is the x vector, if you see, and if this is the x cap vector, okay, then this is going to be our error vector. Okay. And okay, just see that this one essentially becomes I is equal to L plus 1 to m. In fact, this ai, aj's, they are all scalar quantities, so no problem. And here we have j is equal to 1 to L. I am taking this summation, and then it is ai, aj, they remain as it is. And from here we are getting, I mean, what we have done is, oh, this one I have made it wrong. You did not point it out. This is ai qi, okay, because here I have chosen the index to be I, and here I have chosen the index to be j. So, I mean, although I substituted, I should have written down here as the index as I. So, it is ai, aj we have taken from here, but then we are having qi and qj, and basically because qi's are all orthogonal to each other. So, qi qj product is definitely going to be 0 in this case, because here you see that I is not equal to j very clearly, and we are getting this term to be equal to 0. So, that the error is orthogonal to x. And another thing that one needs to observe is about the variance. You see the total variance, if we now look at it, that is to say variance of all the j terms. I mean, if we total variance of the data vector, of the m components of data vector, original data vector. Okay. That variance we can write it as sigma square j, j is equal to 1 to m. All right. So, this is the total variance, and what is that? What is the sigma square expression for us? Remember, lambda j. For us, the sigma square j's are same as the eigenvalues. So, this is equal to summation of lambda j, j is equal to 1 to m. Okay. And so, if this is the variance of the m components, then the total variance of the L elements of the approximating vector x. So, total variance of the L elements of x vector. I mean, if we take the L elements of that, this is summation j is equal to 1 to L sigma square j, which is equal to summation lambda j, j is equal to 1 to L. So, from here we can find out that the total variance of the L minus m elements, okay, this is going to be summation j is equal to L plus 1 to m of sigma square j, which is equal to summation j is equal to L plus 1 to m of lambda j. All right. So, this is the variance that we are chopping off, because what we are doing is that the eigenvalues which are represented as lambda L plus 1, lambda L plus 2 up to lambda m, these eigenvalues are the smallest eigenvalues. So, whatever we chop off out of the L minus m terms, in fact, I mean it will not be very correct to say that this is the total variance of the L elements of x vector. This is one and the same as L elements of A. In fact, we are considering L elements of A, okay. And because we have chopped off the L elements of A vector, okay, the variance of that is also equal to summation of lambda j. So, in terms of the total variance, this is the difference that we are getting by eliminating this lambda L plus 1, lambda L plus 2 to lambda m. And these are the smallest lambdas, okay. These are the smallest lambdas which we are eliminating. So, we are eliminating the minimum variance terms, okay. Mind you, we could have done the reverse also. If we had chopped off the, I mean if we had accepted the extremal solution, because eigenvalue says that it is an extremal solution. Now, somebody can take the first L eigenvalues and chop off the rest m minus L. Somebody can say that no, I will take the first L and I will eliminate the rest, because last class I remember somebody was talking in terms of maximization of variance, okay, that was interesting. And maximization of variance, yes, somebody can do if he keeps the minimum variance terms and chop off the terms contributing to the things, okay. So, that way, I mean even maximum variance solution is possible, but we are going in for a minimum variance solution, and the very fact that it is a minimum variance solution is obtained like this, that order all the lambdas, okay, in the decreasing order and then pick up the first L components of that, take the corresponding eigenvectors, project the x vector onto those eigenvectors, onto those dominant eigenvectors, now we can say, or what we are getting are the dominant principal components. So, the first one to which we have got the projected result is A1. This we will be calling as the first principal component, A2 we will be calling as second principal component, and so on, A3 as the third principal component, and so on, provided lambda 1 is the highest eigenvalue, the corresponding lambda 1 is the highest eigenvalue. So, this is the way. So, by chopping off the L minus m, you are very correct, you are very correct, because m is larger than L. So, we have to chop off the m, I mean we have to chop off the m minus L elements, okay. So, that's very correct. So, this is what we get. So, now this way the dimensionality reduction will be the most efficient, because we are only eliminating the low variance terms by cleverly projecting our data into the Q space. All right. Anyone having any doubt about this approach? Yes, please. In the decoder, yes, the decoder output is getting the X cap components.
So, but there are again n components present. How do we get n components?
You are chopping the A components. Followed. I mean, just look at the encoder and the decoder block again. Okay, I don't want any confusion in your mind. You see, this is the encoder, m elements getting mapped into L elements, right. I mean, it was originally supposed to be m elements here, but I decided to chop off because I am chopping off this in accordance with the minimum variance criteria. Now, I have got this ALs, okay, and using this ALs, I transform these things with QIs, okay, and my summation, the expression that I have got for x vector, okay, says that it is AQ, that is what we are getting as the solution of x.
You should be also n dimension.
Q's are, yes, Q's are of m dimension. Okay, I mean this is a very interesting point, that we are not keeping the m dimensions of L, we are keeping, I mean m dimensions of Q, we are keeping only the L dimensions of Q. So, what is happening to the rest? Okay, the rests, exactly, the rests are all the 0 vectors. Say, you see from Q1 to QL, you are remapping them into Q1, Q2 up to Qm. How? Up to QL you are keeping the original matrix, and QL plus onwards you are chopping off. So, you are as if to say assuming that those vectors are equal to 0 vectors, alright. So, that is why you are getting, I mean as the A transpose, I mean as AQ, as the solution of AQ, I mean that is what we get. Just a minute. We go back to the
Equation number 3.
we go back to the synthesis equation. Yeah, that is what I was looking for. Now, I mean we go back to equation 2 only. Equation 2 is our synthesis equation. You see there some of these vectors forming this Q matrix, they are becoming 0 vectors. Okay. So, but they are still of dimension m. Okay. In fact, in effect what is happening is that you are, I mean chopping off the m minus l elements from here, you are chopping off m minus l elements from here too, okay, but you are keeping them as zeros, and then you are in effect getting the x vector solution.
So, if you are keeping 0, it is obviously going to be of n dimension only. So, what is the use of keeping it 0? Both the sides is going to be 0.
It is violating the order of rule of matrix also. So it should be L only. Except. And
So the padding sum
when
will
we
be
have
0.
estimated error also.
Equation 3, sir. So, look at equation number 3.
1 minute. Yeah, that is right.
We can see that each of those Q's is m dimension. M cross L. It is m cross L.
Yes, yes,
So,
yes.
if you have an m cross L matrix multiplied by L cross 1 matrix, you will get an m cross 1 matrix.
Yes.
Which is what x cap is. So,
Yes.
you get m dimension.
X you have to, x cap you have to get as m dimension.
Put in xl plus 1, xl plus 2 up to xm. So, we directly get from this expression we are getting it x cap as m matrix. Q is m cross L.
Yeah, this point is, no, effectively it is that only. You see that we are keeping the L components of A's, and we are similarly keeping the L components of these Q vectors. So, essentially yes, you are right that these things are all of M. So, these are M by L matrix. So, this is M by L and this is L by 1. So, dimensionally x vector is going to be an M by 1 vector. Okay. So, even after the chopping we really get M dimensional vector. So, that there is no confusion. Okay. So, you do not have to really go into the complication of making those things 0, because those things zeros we do not need it. I mean we can directly take this, okay, we can directly take this, transform it to the QLs, and we get all the x1 to xm's. Is that clear in people's mind now? Okay. So, now yes, one important result what I was telling you is that, So, this is an important result which is of relevance to us in the neural network, that a single linear neuron with Hebbian type of learning Hebbian type adaptation rule for its synaptic weights can evolve into a filter for the first principal component. First principal component's definition I have already given. Okay. So, a Hebbian type adaptation rule, single linear neuron having Hebbian type adaptation rule will give you the first principal component. This is a very important result, and this was pointed out by Oja. Okay, I mean that is the name of the scientist who did that, and the paper where he described this is a simplified neuron model as principal component analyzer, as a principal component analyzer. And this was published in Journal of Mathematical Biology. Mathematical Biology, volume 15, page numbers 267 to 273, and it was a 1982 paper. Okay. So, this is a very interesting result, and we will be accepting this result as it is without going into the detailed mathematical analysis for that. So, in the coming class what we will be doing is that we will take a linear neuron model and go through the Hebbian type adaptation rule, okay, and we will show that how this theory can be expanded into obtaining not just the first principal component, but if we decide to keep L number of output units, in that case we can show that we can extract the first L principal components. Okay. So, whatever we intend to do, okay, through computation can be very easily modeled using the neural networks with Hebbian adaptation rule. Right.